Now, let us talk about the bivariate normal distribution. So, I will introduce the bivariate normal distribution through its probability density function. So, a bivariate random vector x equal to x1 x2 is said to have a bivariate normal distribution, which we denote by n2. It has 5 parameters mu 1, mu 2, sigma 1, sigma 2 and rho. If for some mu I between minus infinity to infinity, sigma I greater than 0 and rho between minus 1 to 1, the joint PDF of x1 x2 is given by this expression, which is 1 by 2 pi sigma 1 sigma 2 square root of 1 minus rho square e to power minus 1 by 2 1 minus rho square x1 minus mu 1 by sigma 1 whole square minus 2 rho x1 minus mu 1 by sigma 1 x2 minus mu 2 by sigma 2 plus x2 minus mu 2 whole square. So, this all in the power of e. Now, one can easily check that this is a proper PDF. What one has to do is, because this is coming and minus 2 rho x1 minus mu 1 by sigma 1 x2 minus mu 2 by sigma 2 is coming. So, if one can make it a perfect square, x1 minus mu 1 by sigma 1 minus rho times x2 minus mu 2 by sigma 2, right. This whole square. So, that becomes this minus 2. Now, plus rho square. So, minus rho square x2 minus mu 2 sigma 2. So, that means plus 1 minus rho square x2 minus mu 2 by sigma 2 whole square. And then one can use the fact that minus infinity to infinity e to power minus 1 by 2 sigma square x minus mu whole square dx is same as sigma root 2 pi, because that we know, because these are normal. This comes from the fact that 1 upon sigma root 2 pi e to power minus 1 by 2 sigma square x minus mu whole square is a normal PDF. And that is what we will do. Sigma 1 is positive, sigma 2 is positive and exponent is there, e to power something is there. So, that means this quantity is non-negative. So, f x1 x2 is always non-negative. I make the transformation z1 is equal to x1 minus mu 1 by sigma, z2 is x2 minus mu 2 by sigma. So, that means 1 upon sigma 1 sigma 2 dx1 dx2 sigma 1 sigma 2 is nothing but dz1 dz2. So, then I becomes minus infinity to infinity. This sigma 1 sigma 2 goes away. So, 1 by 2 pi square root of 1 minus rho square minus infinity to infinity minus infinity to infinity e to power minus 1 by 2 1 minus rho square. Then x1 minus mu 1 sigma 1 whole square is z1 square minus 2 rho x1 minus mu 1 by sigma 1 x2 minus mu 2 by sigma 2 z2 rho z1 z2 plus x2 minus mu 2 by sigma 2 whole square is nothing but z2 square. Now, I try to make this whole quantity as a perfect square. So, this becomes z1 minus rho z2 whole square. So, plus rho square z2 square has come. So, I have to subtract that. So, that becomes 1 minus rho square z2 square. So, that becomes e to power minus this divided by 2 times 1 minus rho square. So, let us try to do this. This becomes 1 by 2 pi square root of 1 minus rho square. Then e to power minus 1 by 2 1 minus rho square. Then z2 square into 1 minus rho square, which is this quantity. And then this perfect square minus infinity to infinity e to power minus 2 1 minus rho square z1 minus rho z2 whole square dz1. Because of the fact that 1 upon sigma root 2 pi, you see I am throughout using the fact that e to power minus 1 by 2 sigma square x minus mu whole square dx is nothing but sigma root 2 pi. So, that is why this would be nothing but square root of 1 minus rho square root 2 pi. This comes outside and so this comes out as a part of outside integral. So, it becomes 1 by root 2 pi minus infinity to infinity e to power minus z2 square by 2. Again, I use the fact that this is a PDF of normal 0 1. So, this has to integrate out to 1. So, the total PDF integrates out to the total f x1 x2 turns out integrates out to 1. So, it is a proper PDF. Now, let us do this result. Suppose that x is x1 x2, which is n2 mu 1 mu 2 sigma 1 square sigma 2 square rho, mu I between minus infinity to infinity, sigma I greater than 0, rho between minus 1 to 1. It is important to know that rho has to be between minus 1 to 1, otherwise that integral which we integrated out will not be finite. If that happens, if x1 x2 has a bivariate normal distribution, then their marginals are normal. If the marginals are normal, then that means mu 1 is nothing but mean of x 1 and sigma 1 square is of x 2. So, these are the marginals. So, this also suggests this result that in the distribution of bivariate normal, the parameter mu 1 is nothing but a mean of x 1. The parameter mu 2 is nothing but mean of x 2. Sigma 1 square is nothing but variance of x 1. Sigma 2 square is nothing but variance of x 2. So, marginals are normal. Not only that, the conditionals are also normal. That means, for fixed x 2 belonging to R, the conditional distribution of x 1 given x 2 is equal to x 2 is normal mu 1 plus rho sigma 1 by sigma 2, x 2 minus mu 2, sigma 1 square 1 minus rho square. And by symmetry, for any fixed x 1 belonging to R, x 2 given x 1 is equal to x 1 is normal mu 2 plus rho sigma 2 by sigma 1, x 1 minus mu 1, and sigma 2 square into 1 minus rho square. So, let us try to see that the MGF of x equal to x 1 x 2 is given by this quantity. For real constant C 1 and C 2 such that C 1 square plus C 2 square is positive, C 1 x 1 plus C 2 x 2 has normal C 1 mu 1 plus C 2 mu 2, and of course, then the covariance term which would be C 1 square, then the variance term. So, it would be same as C 1 square variance of x 1 which is C 1 square sigma 1 square, C 2 square variance of x 2, C 2 square sigma 2 square, plus twice C 1 C 2 covariance of x 1 x 2. So, twice C 1 C 2 covariance of x 1 x 2 is nothing but sigma 1 sigma 2 rho. So, this suggests that possibly rho is the correlation coefficient between x 1 and x 2, and that is what the next part says. Correlation between x 1 and x 2 is rho. So, one very important property of normal distribution is that x 1 and x 2 are independent if and only if rho is 0. That means, we know that if x 1 and x 2 are 0, if x 1 and x 2 are independent, then correlation is 0. But correlation 0 may not imply x 1 and x 2 are independent. But that happens for the bivariate normal case. In the bivariate normal distribution, if the correlation is 0, then x 1 and x 2 have to be independent. This is a very one distinct property of normal distribution. You see, one way to do this would be I can just find the moment density function of x 1 and x 2, and using that I can find the marginal of x 1, marginal of x 2, and so on. So, although in this slides I have provided an alternate proof where I find the PDF of x 1 by integrating out the unwanted variable in the joint PDF, but let me just directly go to, which you can see in the slides, but let me just go to or let me follow the slides. So, what I do is for x 1 belonging to x r, the marginal is nothing but I integrate out the joint PDF, unwanted variable which is x 2. Now, I made the perfect square, if you remember, in f x 1 x 2. So, if I do that, e to power minus x 1 minus mu 1 whole square by 2 sigma 1 square 1 by 2 pi sigma 1 sigma 2 square root of 1 minus rho square, this comes outside, then minus infinity e to power minus 1 by 2 1 minus rho square x 2 minus mu 2 by sigma 2 minus rho times x 1 minus mu 1 by sigma 1 whole square. This comes out. So, this becomes e to power minus x 1 minus mu 1 whole square by sigma 1 square 2 pi sigma 1 sigma 2 square root of 1 minus rho square. Here I take out this sigma 2 outside. So, e to power minus 1 by 2 sigma 2 square 1 minus rho square, then becomes x 2 minus mu 2 plus rho sigma 2 by sigma 1 x 1 minus mu 1 whole square. Now, this is again as if I am integrating a normal PDF at point x 2 whose mean is given by this quantity. So, this quantity I know has to be same as sigma 2 square root of 1 minus rho square, which would get cancelled with this, and of course, root 2 pi would get cancelled with this. So, if you use that, this is what you get. So, f x 1 turns out to be this 1 power sigma 1 root 2 pi e to power minus x 1 minus mu 1 whole square by 2 sigma 1 square, which is nothing but a PDF of normal mu 1 sigma 1 square. So, thus x 1 is normal mu 1 sigma 1 square. Now, by symmetry, certainly x 2 would be normal mu 2 sigma 2 square. Let us look at the conditional PDF of x 1 given x 2. I know that conditional PDF is always proportional to the joint PDF, and the constant of proportionality would depend on at what point the condition variable has been fixed. So, that would be C 1 x 2 times joint PDF of x 1 and x 2, which would be another constant which are there in x1, x2, I absorb C2, x2. I consider their perfect square, which is there. So, you see what would happen is when you make perfect square, e to power minus 1 minus rho square x2 minus mu 2 upon sigma 2 whole square comes, 1 minus rho square gets cancelled with this, and whatever term is with x2 gets absorbed with this. So, I do this is C2 x2 e to power minus 2 sigma 1 I take outside. So, sigma 1 square 1 minus rho square x1 minus mu 1 plus rho sigma 1 by sigma 2 x2 minus mu 2. So, this is clearly, if I consider this as a function of x1, this is clearly a PDF of normal with mean as this quantity and variance as sigma 1 square 1 minus rho square. So, clearly for a fixed x2 belonging to R, f of x1 given x2 is a PDF of normal mu 1 plus rho sigma 1 sigma 2 x2 minus mu 2 and sigma 1 square 1 minus rho square distribution. So, you can see over here expected value of x1 given x2 is equal to x2 turns out to be linear. It is a linear function of x2. The third follows from the second on using symmetry, because x2 given x1 is the same. Now, let us try to find out the joint moment generating function. So, mx1 x2 is same as expected value of e to power t1 x1 plus t2 x2. Now, I know that expectation is same as expectation of a conditional expectation. So, expectation of a conditional expectation with respect to x2. Now, here x2 is a fixed quantity, because it is with respect to conditional distribution of x1 and x2. So, e to power t2 x2 goes outside and it becomes expected to e to power t1 x1 given x2. But I know that x1 given x2 is has a normal distribution. So, that means this is nothing but MGF of normal with certain mean and variance, and mean is nothing but this and variance is this. So, it is MGF of this normal distribution. So, that means x value of t1 given x2 is equal to x2 turns out to be e to power mu 1 plus mu t, the mean times t. So, e to power mu 1 plus rho sigma 1 by sigma 2 x2 minus mu 2 at the point t1 plus sigma square, which is sigma 1 square 1 minus rho square t1 square by 2. So, this quantity turns out to be this. So, I have to put here small x2 as capital X2 to get this quantity. So, that is what I do. So, this would be X2. So, if you simplify this turns out to be this quantity. Now, I know that X2 is normal mu 2 sigma 2 square. If x2 is normal mu 2 sigma square, though, that means this is nothing but MGF of normal mu 2 sigma 2 square at this point. So, we do nothing but e to power mu 2 times this plus sigma 2 square, this quantity square divided by 2. So, I do that. So, e to power t2 plus rho sigma 1 by sigma 2 t1 mu 2 plus this quantity square sigma 2 square by 2, then this quantity square t2 plus rho sigma 1 by sigma 2 t1 whole square by 2. So, you simplify this is what the MGF turns out to be, e to power mu 1 t1 plus mu 2 t2 plus sigma 1 square t1 square by 2 sigma 2 square t2 square by 2 plus rho sigma 1 sigma 2 t1 t2. Now, to show that all linear combinations have a univariate normal distribution, so let C1 and C2 be real constants such that C1 square plus C2 square is positive, and let y is same as C1 x1 plus C2 x2. I have to show that distribution of y is univariate normal. To do that, I consider the moment generative function of y. So, for t belonging to R, myt is nothing but x to e to power ty, which is same as x to e to power tc1 x1 plus tc2 x2. Now, if you look at this is a joint moment generating function of x1 and x2 at the point tc1 and tc2. Now, moment generating function of x1 and x2 we have derived. So, e to power mu 1 t1. So, that means e to power tc1 mu 1 plus tc2 mu 2. So, that is what t becomes common. So, this one plus t square c1 square sigma 1 square. So, t square goes plus t square c2 square sigma 2 square. So, t square goes outside plus twice rho tc1 tc2 sigma 1 sigma 2. So, t square again goes outside. So, this one is. But if you try to see this is nothing but the MGF of the type e to power mu t plus sigma square t square by 2, which is MGF of normal with mean as mu. Mu is nothing but C1 mu 1 plus C2 mu 2, and variance is given by C1 square sigma 1 square plus C2 square sigma 2 square plus 2 rho C1 C2 sigma 1 sigma 2. So, what we see is the linear combination of bivariate normal random vectors, random variables is univariate normal. Now, we will see that converse is also true, that if you have a random vector such that all its linear combinations have a univariate normal distribution, then the joint distribution would be bivariate normal. Let us try to see what is, because we have already seen that x1 is normal mu 1 sigma 1 square. In fact, we have seen xi is same as normal mu I sigma I square for I is equal to 1 to 2. So, variance of x1, that means is nothing but sigma 1 square, variance of x2 is sigma 2 square. Now, let us look at psi x1 x2, which is log of mx1 x2 t1 t2. Then covariance of x1 x2 is nothing but, I differentiated twice of psi of x1 x2, which is log of mx1 x2, and put t is equal to 0. Now, psi x1 x2 you know would be given by log of this quantity, which is nothing but mu 1 t1 plus mu 2 t2, mu 1 t1 plus mu 2 t2 plus sigma 1 square t1 square by 2 plus sigma 2 square t2 square by 2 plus rho sigma 1 sigma 2 t1 t2. Now, you can differentiate with respect to t1 and t2 and then put t is equal to 0. So, you will see that all these terms will not contribute and only you will get rho. So, if you do this, you get this as rho sigma 1 sigma 2. So, covariance x1 x2 turns out to be rho sigma 1 sigma 2. So, rho of x1 x2 turns out to be covariance x1 x2 divided by square root of variance of x1 current of x2, which is nothing but rho. Let us look at the seventh part. We know that independent random variables are uncorrelated. It follows that if x1 and x2 are independent, then rho is equal to 0. So, that holds for any distribution. But what is very distinct about normal is bivariate normal is, if correlation is 0, then they are x1 and x2 are independent. So, conversely, suppose that correlation which we have seen is nothing but rho is 0. Then when I look at the joint PDF, that cross product term will vanish, because minus 2 rho x1 minus mu 1, 2 rho x1 minus mu 1 by sigma 1, x2 minus mu 2 by sigma 2, that would vanish, and you will get PDF as this, which can be. So, here you can see you can separate out the terms of x1 and x2. In fact, you can write down this as fx1 x1, because these are normal mu 1 sigma 1 square density, fx2 sigma 2, which is part of this, which is coming because of normal mu 2 sigma 2 square. So, if correlation is 0, that would imply x1 and x2 are independent. So, this is bivariate normal distribution is one distribution where if correlation is 0, then x1 and x2 are independent. Now, we have seen for bivariate normal distribution, if you consider any linear combination that has a univariate normal distribution. In fact, this property characterizes the bivariate normal distribution. What it says is that x1 x2 be a bivariate random vector with mean as mu I, which is finite, variance of xi as sigma I square, which is again finite, and suppose covariance of x1 and x2 is rho, this will be correlation of x1 and x2. So, this will be correlation of x1 and x2 as rho, which belongs to minus 1 to 1. Then x has bivariate normal distribution with parameters. Of course, parameters have to be the mean mu 1 and mu 2, variance sigma 1 and sigma 2 square, and rho as correlation. If and only if for any real constants t1 and t2 such that t1 square plus t2 square is greater than 0, their linear combinations has univariate normal distribution. Of course, once you know that it has a univariate normal distribution, then you know that parameters are its mean, which would be t1 times mu 1 plus t2 times mu 2. So, that is the mean. What is the variance? T1 square variance of x1, so t1 square sigma 1 square, plus t2 square variance of x2, so t2 square sigma 2 square, plus twice t1 t2 covariance of x1 x2. So, twice t1 t2 covariance of x1 x2 is nothing but correlation times product of standard deviations. So, what this result says is a random vector, a bivariate random vector has a bivariate normal distribution if and only if all its linear combinations have univariate normal distribution. So, let us try to do one part. We have already seen that if x1 x2 has a bivariate, then all its linear combinations have univariate normal. Now, conversely, suppose that we have constants T1 and T2 such that T1 square plus T2 square is positive, and x1 x2 suppose has a bivariate normal distribution. And no, suppose all linear combinations have univariate normal distributions. I have to then show that x1 and x2 has bivariate normal distribution. To do that, I consider the movement generating function of x1 and x2. So, for t is equal to T1, T2 belonging to R2, I consider movement generating function of x1 and x2 at the point T1 and T2, which is same as expected value of e to power T1 x1 plus T2 x2. But I know that T1 x1 plus T2 x2 is y, which is univariate, has a univariate normal distribution. So, it is the movement generating function of y at the point 1. So, which is same as my1. But myt I know is same as e to power mu t plus sigma square t square by 2. So, t is 1. So, it would be same as e to power mu plus sigma square by 2. So, e to power mean, which is T1 mu 1 plus T2 mu 2 plus sigma square by 2, which is T1 is sigma square plus T2 sigma 2 square plus twice rho T1 T2 sigma 1 sigma 2 by 2. But this is nothing but MGF of bivariate normal distribution with parameters as mu 1, mu 2, sigma 1 square, sigma 2 square and rho. So, what we have shown is the joint MGF of x1 x2 is same as that of n2 mu 1 mu 2 sigma 1 square sigma 2 square rho. So, by uniqueness of MGF I can say that x has n2 mu 1 mu 2 sigma 1 square sigma 2 square rho. Now, before I end this module, let me give the following take home problems. So, let x equal to x1 x2 x3 has a multinomial distribution with n and theta 1 theta 2 theta 3. Find the conditional PMF of x1 x2 given x3 is equal to x3. The second problem, let x1 and x2 be independent random variables such that xi has normal mu I sigma I square. Find the distribution of y, which is x1 plus x2 comma x1 minus x2. So, this was all for this module. Thanks for your patience and have a great day.